Hello everybody, welcome back to this month's Future in Space Hangout. My name is Tony Darnell, and after weathering hurricanes and cleaning up after them, I am back, and we are online, and we are the world headquarters of Deep Astronomy Space is now active. So it's good to be back. It's good to see you be back to talking about astronomy and science. And today, as we do with every Future in Space Hangout, we talk about what else but the future in space. And today, we're taking another look at a mission we talked about last year, which is the Habitable Exoplanet Imaging Mission. And these guys, as its name suggests, want to image exoplanets. So we're going to talk about how they're going to do that, or how they hope to do that, and with what equipment. And it's, for short, it's called HabEx. And so that's what we're going to be talking about today. We are live on 4 platforms: YouTube, Twitch, Facebook, and Periscope. And I am looking at 3 of those 4 platforms right now. My good friend Carl Clark, congratulations on his new job, but unfortunately that means he can't help me drive the internet. So I'll be doing my best to look at all of these different things, but we do want you to ask our guests questions and leave comments by using all of the various chat methods. I'm already on YouTube, and I saw John Suffel earlier. There he is, Catherine Peterson, and Joe Schmo. Good to see Joe Schmo's back on YouTube. And so please leave your questions and comments there, and I will be happy to read them out during the discussion. So without any more ado, let me bring up my co-host. I've got so many buttons to push this time. Dr. Harley Thronson, who helps put these together. Hi, Harley. How are you?
Doing well, Tony. Always good to see you. See that the Deep Astronomy Nerve Center is back and functioning.
That's right. We are live. Yep. The world headquarters, deep in the swamps of Florida.
Swampier now than maybe it was a month ago.
Yes, that's right. A little more swampy than it was before. And a little bit more treeless as well. So as we do each week, Harley, why don't you go ahead and give us an introduction into this hangout, as well, you know, what we're doing and why each month, and maybe introduce our guests.
You gave us an excellent start. I'll have the guests introduce themselves and get a little bit of background, professional background to each of them in just a moment. For the regulars here, you know that we've had this group. We've had representatives of the HabEx mission on about a year ago. Put them in context. About 2 years ago, NASA headquarters, the Astrophysics Division, began funding a quartet of design concepts, the science cases, engineering, technology priorities, and so on, intended to, in about a year and a half, be submitted, reviewed, and assessed by the National Academies as part of their 2020 Decadal Survey. That event is a major watershed for future astrophysics missions. The National Academies will, as I said, in about a year and a half or so from now, begin assessing the importance of 4 of these mission concepts. We've spoken already here about the other 3. Today we're going to be talking about, this afternoon, we're going to be talking about the Habitable Exoplanet Imaging Mission. Very exciting. They all are. So it is a terrifically exciting mission, as our 3 guests will be describing. So what I'd like to do is have each of the 3 introduce themselves briefly, and then we'll go back to Leslie and have her give an overview of the HabEx mission. But first, Paul and then Stu, why don't you guys give us each a 30-second description of your professional background.
Okay, I'm Paul Schoen. I'm an astronomer, an astrophysicist at the Arizona State University in Tempe, Arizona. My experience has been focused basically on the problem of understanding star and planet formation, both within our galaxy and nearby galaxies, over my professional career. I've also got involved in an awful lot of instrument design and building and mission design. I'm building instruments right now for flight and for use on telescopes here on the ground, and I also am involved in designing and building CubeSats as well right now. So a lot of really interesting stuff out there, and the role that I play on HabEx is that I'm the lead on the ultraviolet spectrograph instrument, and that is one of two general astrophysics instruments that complements the primary mission of exoplanet direct imaging.
Thanks, Paul. Stu?
Hi, yes, I'm Stuart Shacklin. I've been at JPL for 27 years. I'm the supervisor of the high contrast imaging group here, which means my group and myself work primarily in methods of directly imaging and characterizing planets, exoplanets, planets around other stars. My main roles on HabEx are in the performance estimates, well, the design of the Chroma Graph and of the star shade, the characteristics of those devices, the performance evaluation of them, error budgets, and also the design reference missions. So kind of the sequencing of observations and which stars will we look at, those aspects of it.
Very good. Thanks, Stu. And just before I hand off this to Leslie, who will give an overview of the HabEx mission, just a note for the audience: our plan is to return to all four of the missions in a year from now, follow them through the National Academy's process. So those folks who are interested in how NASA and the science community identifies the priority missions for its future, just tune in over the next couple of years. So we will be coming back to everybody as the missions evolve. So Leslie, please introduce yourself and tell us a little, in fact, tell us as much as you wish about the HabEx mission.
Sure. So my name is Leslie Rogers, and I'm an assistant professor at the University of Chicago. I've been here for a year now, and before that I was a postdoc at both Berkeley and Caltech. And in my research, I primarily model the interior structure and formation of exoplanets. And I'm trying to distill from the observations we can make of exoplanets what planets are made out of, which are rocky, which are gas giants, and the wide array of diversity of potential planet compositions that might exist. My role in HabEx is I'm lead of the Auxiliary Information Working Group. So part of that working group is some of our main goals are to figure out exactly how many observations HabEx will need to determine the orbit of any planet that's discovered, as well as what kind of precursor or contemporaneous observations should be prioritized to complement the HabEx mission itself. So let's move on to discuss HabEx, and maybe we can go to my first slide.
Okay, hang on just a sec. I want to, but before you do that, Leslie,
Sure.
I want to just get everything set up here. So we're getting ready to talk about HabEx, but you know, as we have done so many of these hangouts where we talk about the Decadal Survey. We've talked about the Decadal Survey itself. And what I want to know from you guys before we move on to HabEx is, why can't they all just be on the Decadal Survey? Why does there have to be a choice made among the four instruments? Why can't they all be there and then just have them be ranked accordingly? Can that happen? Or because, you know, usually Decadal surveys have a lot of different priorities, right? Anyone?
Who wants to step into this one?
Huh?
Well, actually,
you don't want? Is it too political? Okay. Well, I would just.
All four of us may have a slightly different answer. One is that what the Decadal Survey and, of course, NASA, just FYI, the Decadal Survey in Astronomy and Astrophysics also advises NSF and occasionally the Department of Energy on their.
That's right. It's not just NASA stuff.
Correct. And they face a situation that, and they handle it in different ways. There's limited funding for it, so there has to be some type of prioritization in that. Sometimes it's a prioritization in time that all the missions are worth doing. Actually, I think all four of these concepts are going to be worth doing. I think it's unambiguous.
I know, that's what I was getting at too. It's like, what?
So there may be a prioritization in time. There may be a due to budget. There may be a prioritization due to the technical readiness of the design. Some may be more advanced, less advanced. Some technology may be ready or not. Some missions may be combined, uncombined, or so on. And in fact, and this is just for us history geeks, the 1990 Decadal Survey, I think the 2020 will be the seventh, but something like that. But whatever, the 1990 Decadal Survey faced exactly the same problem. There were, depending on how you count them, 4 or 5 concepts that were all bunched up together, and what they ended up doing was saying, you all will be launched. We're just going to do them at different times as the money's available. So that, and my colleagues here may have a different perspective on it, but it's basically limited resources of time or money.
Just can't afford them all, huh?
Yeah.
Well, you know what I think they should do then? I think if this is how it's going to be, then there needs to be an awards ceremony where they have it like the Academy Awards, and they go, okay, the nominees for the number one spot in the Decadal Survey are...
By the way, no joke, that comes pretty darn close to what actually happened.
Yeah, I'm sure it does.
It's not broadcast, and nobody other than the astronomy community cares.
It would be a geeky show, wouldn't it? I don't think you'd get the viewership that like the Emmys get or something.
I will bet you that the results, however, will be webcast. I will bet this time they will have some type of presentation on the web.
Call them the Deckies. The Deckies. From the
likely no red carpet.
We may have other things to talk about. In any case.
Okay. All right. Well, let's get to HabEx then, folks. And Leslie, you were about to go into an introduction into this mission. So what do you want me to pull up? You want me to pull up your
the very
PowerPoint?
First slide.
Oh, okay.
Yeah.
Let me get rid of all this other extraneous stuff. And there we go. Okay. Let me.
Yeah. So I wanted to start with this image.
This is an image of Saturn.
It's an image of Saturn taken by Cassini, but where the Cassini, yes. So this is in honor of Cassini's grand finale last week. But actually, this is the Cassini spacecraft taking an image both of Saturn and the Earth. The Earth is that little blue dot in the lower right corner. And Cassini was able to do this essentially using Saturn as an external occulter blocking the sunlight so that it could resolve kind of the Earth from the glare. And HabEx essentially has to be a lot more clever to try to image Earths around other distant stars. We won't necessarily have a serendipitously placed planet in front of us to use, but rather HabEx will use both or one of either an internal Chroma Graph that is kind of in the telescope itself and will block some of the light from most of the light from the host star, or a star shade, which Stuart will talk about a bit later.
So this is an example, Leslie, right, of seeing a very dim thing next to a very, very, very dim and small thing next to a very big and bright thing.
Exactly.
Yeah, okay.
Yeah. And so an analogy is to kind of take an image of an Earth around a sun-like star, essentially is analogous to detecting a baby firefly in the glare of a huge Hollywood searchlight when they're located in San Francisco and you're in New York City on a cloudy day.
Oh, so that doesn't sound hard.
No, it's incredibly difficult. And so I'm always tremendously impressed by what Stuart and his engineer kind of colleagues managed to accomplish.
So that's the physical problem that HabEx has to overcome.
Exactly.
The physics. Yeah.
And then once we actually detect these distant Earths, then we want to study their atmospheres. So if you move on to the next slide.
Pew. Look at this high tech, folks.
Yeah, awesome.
Okay, I'll do the sound effects too.
So this is actually a spectrum of our own Earth. And by spectrum, in this case, what it's showing is how the Earth is reflecting different colors of the light from the sun. And due to the presence of molecules and other species in Earth's atmosphere, some colors of light are more reflected by the Earth's atmosphere, and some colors of light are less well reflected. And that's what essentially the wiggles in this blue line represent. And that, so this is called a reflection spectrum, and the various shapes and locations in terms of colors of the features in the spectrum can allow us to identify molecules in a planet's atmosphere. And so you can see this figure is credited to Ty Robinson, who's another one of the STD members. And you can see he's labeled all the various features on this diagram as due to either a water molecule, ozone, that's O3, oxygen, O2, carbon dioxide, CO2. And so part of what HabEx really wants to do is not only discover these distant Earth-like planets, but also to characterize their atmospheres to get a spectrum breaking up the light from the planet in all these different colors to hopefully identify various molecules in the atmosphere.
Okay, but wait, this isn't a spectra, is it? This is a reflectance graph.
Right.
These aren't spectral lines, are they? Or are they?
They effectively are spectral bands of the various molecules, but instead of, everyone might be more familiar about kind of spectra applied to like absorption.
Yes, that's what I am.
Certain molecules kind of absorb various wavelengths of light. But you could also plot a reflection spectrum like this, where like certain molecules will reflect light at certain wavelengths better than others.
Okay,
and
so really you can only see this. Will HabEx be able to resolve the planet disk, or will it just look at the reflectance of a more or less a point source?
HabEx will just look at the reflectance of more or less a point source.
Okay, all right, thank you. So yeah, this would be a spectra then, more than a reflectance.
Yes,
okay,
exactly.
I see. Okay, and this is at about 1 micron, so we're looking at the near infrared.
Yeah, the near infrared and the visible, and Paul will talk a bit more about the UV as well.
Okay. Okay. Good. And, did you want me to go to the next one, or do you want Paul to? Do you want to say something?
Yeah, I was going to suggest, and Leslie, keep on going, or pass it off to Paul. I wonder, do we have an image or artist conception of what HabEx is proposed to look like as a spacecraft?
I don't have one handy in my slide decks. Paul or Stuart, do you have one?
No.
I just thought of that.
Yeah, sorry.
I tell you, I think that might be, and we can get to it. And I wonder if Stuart or Paul, I wonder if one of you guys could dig up on the very. By the way, this mission, like all the other missions, this concept has got a terrific website, trivial to find.
That's right. I put the link in the description box. It's jpl.nasa.gov/HabEx.
Yeah.
So
very easy to find. In any case, maybe one of you guys could, or while we're talking, Tony, I wonder if you could find an image. It might be a helpful artist conception.
Well, I'm on HabEx. I'm on the JPL site now, and it's a really pretty site. But to see it, here, let me just try. I have to add a shot. Thank you, Harley, for adding work to me. Thank you. No, really. Let me just get
Stuart's video might give a bit of an indication as well. I mean, the truth is that at this stage, we're in the process of writing our interim report.
Right.
And studying kind of one out of the two architectures that will eventually be studied. So we don't necessarily know 100% what the absolute final version of HabEx will look like.
Okay, here's the website, and as you can see, it's really nice. It's a great website, but there's a spacecraft. Can you see it? So it looks like
that's a small spacecraft. That's not HabEx.
That's what?
That's spacecraft from a earlier version.
That's not even HabEx. Okay, where should I go? Let me just see here. Technology.
That's a good question.
Okay, well, as we are, I will try to find us a picture of HabEx, but let us continue with our hangout. So these are the kinds of things that that you're going to be doing, among others, with HabEx. Right. On the one hand, you want to see these very faint. We're talking about actually imaging these planets, folks. We're not talking about inferring their existence by wobbles or dips or any of that. We're talking about actually looking at
You're
the planet
actually
itself.
collecting the light that's coming from the planet itself, that's being reflected off the planet.
And that's something that is exceedingly
Pretty
important.
amazing.
Yeah, that'll be really nice. I don't even think JWST will be able to do that. It'll be able to take spectra of atmospheres, but not image the planets. Well, it might. I mean, I keep getting different answers for that. It might actually image it, but
not around sun-like stars, so not a true Earth twin.
Okay, so
you do need HabEx to do that.
Okay, and here's where you want to look with it. Is that right?
Well,
maybe.
Well,
those are just the closest stars.
These are the closest stars. So here, another component. So HabEx, in its broad survey, looking for other Earths, will look at more stars than this, out to a greater distance than this. But another component of HabEx's science case is to do a deep dive and really get to know our nearest neighbors the best that we can.
Okay.
So for some subset of these nearest neighbor stars, we're going to monitor them far more closely and deeply so that we can find essentially as many planets that exist around them as we can.
Well, this will be exciting. Proxima Centauri, all these a lot of stars. Some of them aren't even, well, maybe they are listed here. But yeah, there's a lot of interesting things that we want to look at with HabEx. Okay, so
yeah.
Is that a pretty good intro there, Leslie?
Yeah.
Or was there more you wanted to say?
No, I think that pretty much summarizes the main branches of the exoplanet program. But then general astrophysics is also a crucial part of the HabEx mission.
I'm sorry, what astrophysics?
General astrophysics.
Okay.
So other non-exoplanet astrophysics.
So help me, and I know we've talked about this before, I'm reminding myself, HabEx is not a wide field instrument, is it? It's going to be looking at a relatively tiny part of the sky, right?
You're talking about the primary field for the exoplanet work, or are you talking about the general astrophysics?
Well, let's talk about that. Are there different fields of view for different science?
Yes, there are. There are different instruments. The general astrophysics portfolio currently is carrying two instruments, a wide field imager and an ultraviolet spectrograph. And in both cases, the wide field is 3 arc minutes on a side square.
Wow.
And so you might think that there are certainly instruments and facilities that have a much wider field of view than that. But 3 arc minutes at the limiting resolution of a 4-meter space-based telescope is a pretty big image. It's a pretty big picture.
A big field of view, yes.
Camera or with that spectrograph.
That's about 1/10 of the diameter of the sun.
Yes.
The apparent diameter, yes.
Yes.
Okay, right. Yeah, okay, good. Thanks for putting that in perspective. And the other field of view then with the UV spectrograph, what is it going to be?
That's about the same. It's also about 3 arc minutes square on a side, but a spectrograph is a different beast, right? It takes the light and disperses it to do exactly like you're used to doing in your high school physics experiments of taking sunlight and breaking it out
high school with
to its composite colors. But we do it in the ultraviolet to break out the colors of the light there. And we're doing this with a design that uses what's called microshutters. This is similar to what they're doing with JWST, right? Which is the idea that you can take a field of view, a square field of view, and you can pull out different parts of that field and relay that on its own through the dispersive mechanism of the spectrograph and produce a spectrum. So the idea is you can take multiple spectra, multiple objects can be studied in one shot, in one pointing. And that's what the goal, or one of the goals of the ultraviolet spectrograph is.
Multiple spectra in one pointing. Does that mean if there are, like in TRAPPIST-1, all of those planets, you get multiple spectra in that system? Or are you talking about anything just happens to be in the field of view?
Well, anything in the field of view. The problem with TRAPPIST, right, is that everything's so close into the star that it's really hard to separate them out as individual pointings, right?
Is it?
The
Okay.
shutters would have to be incredibly small to be able to do that. Now, the design for the ultraviolet spectrograph is really focused on the complementary capability that we're looking to deliver with HabEx, which is to provide a general enough astrophysics portfolio that this would be useful to the community as a whole. This, of course, is a very challenging thing when you're talking about building or designing an observatory that's going to fly 20 years from now, to understand the capabilities that would be necessary for the cutting-edge, compelling science 20 years from now.
And for the community as a whole to agree on what it wants.
Yes, indeed. Yes. So what we try to do is we try to look at where the perceived challenges are going to be. Ultraviolet in and of itself is a challenge, right? You can't do this anywhere else but in space.
That's right.
Our atmosphere absorbs everything.
And Hubble does it now with the EUV, but that's it.
That's it. And at some point, unfortunately, in the near future, Hubble is not going to be there to do it for us. So we're looking at restoring a capability in the late 2020s, 2030s that will have been gone for a while.
That's true.
Right,
and you know, it's weird because we're taking this sort of detour, a necessary detour, into the infrared with JWST and LUVOIR and things like, well, maybe LUVOIR will do some UV too, but you know, but that's the same time scale, what you're talking about, late 2030s.
All four of these, right? I mean, you were talking about what the Decadal is going to do. It's going to take these four
missions. We're calling them the Deckies now.
Whatever you call them. They're going to take those and they're going to look at them and they're going to try and figure out which of them provides the best bang for the dollar, provides the most compelling science, really opens up doorways that we don't have open to us right now. So there's going to be a prioritization that comes out of that. But it's not just what we're working on, right? The Decadal looks at all kinds of other stuff as well, to do with ground-based astronomy, to do with other stuff that is maybe probe-class missions or that kind of thing. So there's a lot of really neat science that could be done in the 2020s, 2030s. It takes that long to build one of these things, right?
Yep, that's right.
Typical duty cycle from a Decadal saying, yes, this is what we're going to do, to actually putting the thing in space is like 20 years. So that's what could very well happen in this particular case. We would look to accelerate it as much as we could, but that's the problem. But with the astrophysics portfolio on HabEx, what we're trying to do is provide a set of capabilities that will be valuable. They're modeled on or designed around specific problems that we know we understand right now that people are going to want to try and do. But as with Hubble, and probably what will happen with JW, some of the best discoveries will come out of stuff that we haven't even got a clue about right now. And so it's a matter of designing the capability in there, building it, if you like, and having the science come to be done and to be executed and to further our understanding and learning about the universe.
Very true. I mean, the examples would be Cassini finding Enceladus and all the interesting things there. We didn't expect that before it launched, and of course Hubble has done it so many times we don't even keep track of that anymore. So yeah, that's an excellent point. Well, Stuart, let me get you in on this. You're a member of the High Contrast Imaging Group, and Larry Keese is, or no, I'm sorry, not Larry Keese, Muppet Rathbun, good handle. So we are seeing optical data, seeing the light reflected off the planets. And we, as Leslie told us, that we are actually going to be looking in the optical and near infrared. But you've got the task, apparently. High contrast is the key word here in this, isn't it? You've got to somehow get that image in the field of view such that it can be imaged. So can you talk a little bit about the challenges involved in that, and maybe we could throw in some starshade talk while we're here?
Sure. Yeah, that's the great challenge, is that we have a very, very faint signal. And if you could bring up one of my slides, I think if you went to the Chroma Graph presentation and go right to the second slide.
This one? Let me get rid of that. Let me get rid of that. Okay. This one?
The next slide.
Okay. Here we go.
There we go. That's a picture that shows the spectrum of a star, and the wavelengths, like Leslie showed, are across the bottom, and
that's this curve here.
That's the upper curve.
Yeah.
And then below that, way below that, is the spectrum of a planet.
Look at all these orders of magnitude.
Yeah. This is
one of
really
those steps is a factor of 10.
Yeah.
Okay. And so the planet is 10 billion times, a planet like Earth is going to be 10 billion times fainter than the star.
Yeah.
That's that ratio right there. Now, if we could, we'd go, and there was a mission that we looked at to do this. We'd go to the thermal infrared off to the right side of the chart where that smaller arrow is, because there the ratio, if you go to 10 microns, the ratio is about 1,000,000 to 1. So it's a lot easier. But the problem is that at those long wavelengths, the telescope has to be much, much larger to be able to separate the planet from the star. The resolution isn't as good in the infrared.
And what are we talking about here with objective size on HabEx?
HabEx we're looking at two versions of HabEx, a 4 meter and a 6.5 meter.
Okay. So presumably the 4 meter would be enough here.
No, at 10 microns, on the right side of the chart there, it's more like a 40 meter.
Oh.
Maybe enormous.
Huh? So wait a minute. We're not going to see this with HabEx then.
That's right.
Oh, okay.
Not to see the red. We'll be off on the left side over there.
Okay, over here.
The ratio is much, much less favorable. It's 10 billion to 1. But the telescope resolution lets us separate the planets from the stars in angle, right? We can resolve them out. And so the great challenge is that the planet is very, very faint, and it's right adjacent to the star. So, imagine driving down the road and you see some glare from your windshield, whatever. It's, there's the glare is our sworn enemy here. And the closer you are to whatever's producing the glare, the worse the problem. So that's where these coronagraphs and star shades come into play. And a coronagraph is an instrument that's designed it allows the starlight into the telescope, but once it gets in the telescope, you have to try to block the starlight without blocking the planet light. And so that's where all the instrument design comes in. And the star shade, on the other hand, is an instrument that blocks the light before it gets into the telescope. Okay. And they both have their advantages and disadvantages that we can talk about.
Okay. Well, do you have an example in your slides about a coronagraph before we go to starshade?
Sure. Let's go down. And by the way, that ratio 10 billion to 1. If you could go down to slide 6, we'll start there. But that ratio 10 billion to 1, the example I like to use of that is that's the ratio of a bump 1/100th of the thickness of a human hair on the slopes of Mount Everest.
As seen from the slopes of Mount Everest, you mean?
Yeah. Imagine you're trying to measure a bump that's that thick against the slopes.
Oh, wow. That's a good visual.
It's actually on the slopes because that's how close the planet is to the image of the star.
So one of the climbers' hair.
Slopes. Okay. So when light comes into a telescope from a distant source, like a star, which is essentially a point source here, it doesn't form a perfect image, a perfect point. It forms an image that has rings around it, and those are called diffraction rings, and that's what you see in the middle of the image. And then the blue line, the blue curve there that you see, that's showing how bright those diffraction rings are. So that's kind of the slopes of Mount Everest compared to the peak of the image, where most of the starlight is centered there at the middle. And you can see that where the planet will be, which will be 2 or 3 of these little diffraction rings away, it's maybe it's 10 billion times fainter than the star itself, and it's maybe 10 million times fainter than those rings. And so the coronagraph is an instrument that's designed to do 2 things. It's designed to remove those rings, and then once you've removed the rings, you still have scattered energy that's left because the telescope optics aren't perfect. And so then there are parts of the instrument that are designed to deal with that scatter and remove that scattered light, so that ultimately you push all that, where that blue line is, you push that all the way down to the level of the planet so that you can see the planet there. And so if you go down, I think to the next slide, there's an example of I don't show the whole chronograph instrument, but this is the type of chronograph that we're baselining for HabEx, and it's called a vortex chronograph. And what it does is you focus the starlight onto this little mass called a vortex, and it sets up a pattern. It works in polarization such that the light tends to cancel itself out as it continues to go past this mask. And the way it cancels itself out is that all of the starlight that was right on axis, if you were perfectly centering the star on axis, all of that starlight goes to a place where you can completely block it downstream. That's kind of what that upper right plot there shows, that kind of volcano with the hole in the middle. That hole is where there's no light, and all of the light from the star got reshaped to where it's outside of some region, and then it can be blocked. And so then when you take the light of
what is this FT? Is that Fourier transform? What is that?
That's a Fourier transform.
Okay.
That's right. Fourier transform of that function. So if you were to take a planet and put it not right on axis where the star is, but a little bit off to the side, because it's in orbit around the star, then it doesn't see the vortex the same way. It sees only a little piece of it off to the side. And so that light from the planet can go right through the middle of that volcano-looking function, and it goes right through to the detector. So that's a way of letting us remove those rings, those diffraction rings. Those are all that get reshaped into that volcano function, and then it lets the planet light go straight through. So that's kind of the trick that we're employing for HabEx, and there are other kinds of chronographs that work better or worse on different kinds of apertures.
Okay. All right, and let's talk a little bit about the star shade now. Can we do that?
Well, I'll tell you what. Why don't we go? There's if you go to, then I guess if you were to go to, if you could slide 5 of that package that you're in right now. There you go.
Uh-huh.
That's a picture of what the inside of a chronograph looks like in our test bed. So just to give you an idea that there's that little thing, it's called the filter. Of course, you can't see the filter, but it's labeled. That's where that little mask would go. And there's a series of other masks in the system as well.
And all it is just a little thing that blocks out light. That's it.
And this particular one actually just kind of reshapes the light. It actually lets the light through, but it reshapes it, and then so where you can block it downstream. But then there's something else in there that's labeled that's called a DM. That stands for deformable mirror. And the deformable mirror is what we use to reshape the wavefront that's gone through the system. So the starlight comes in, and instead of being a perfect plane wave, it's kind of distorted. And so this DM has the opposite shape so that it removes the distortions and lets the wavefront.
What's it distorted by?
Oh, by the imperfections in the optics. So
okay.
You could have the mirror could not be perfectly shaped. It might have a little defocus, or some from where it's mounted. It could have astigmatism and coma and other aberrations. It could have defects in it in the coatings. It could have any dust on it. Any number of things can distort the wavefront, and all it takes is subatomic levels of distortion, and the chronograph won't be able to see planets like the Earth around other stars.
And so this DM is gonna determine, or something's gonna determine what the deformation is, and then correct for it with that.
Right. We actually move the DM a little bit and change what we see in the image plane. Right. We change what the image looks like, and from that we can determine how to move the DM so that we cancel all of that unwanted light, that glare that came through to the image plane.
Okay, so this is using coronagraphs and deformable mirrors to get high contrast imaging, to see what Leslie was talking about, the very dim, small thing next to the really big, bright thing.
And so it makes for a somewhat complicated instrument, and it also makes for one that has to be very, very stable, all the way from the front of the telescope, all the way through to where all of these masks and the DMs, these deformable mirrors, are located.
Okay, so well, that reminds me. Larry Keyes was asking me early in the Hangout, where are you going to put this thing? What orbit?
Well, this is going to be out at what's called Earth-Sun L2.
L2, okay. So it's going to be out with JWST.
It's about 1 million miles. That's right. The same place as where JWST is, about 1 million miles away from the Earth, past the Earth, in an orbit that has a 1-year period.
Okay. All right. Cool. And this is your test bed, and how's it going? Is it going to work? Are you able to get it to work?
It looks fantastic, actually. It's working for a different mission. We're working on a chronograph for the W1 mission, and that chronograph has pretty much met all of its milestones so far. It's already doing part per billion rejection of the starlight, and it's doing it in bands that are sufficient to do the spectroscopy that Leslie was talking about.
So WFIRS is the Wide Field Infrared Survey Telescope. It's going to be launched here in the next decade or so, and they're building it now, and it's going to be a wide field, as its name suggests. And
Well,
and
it'll
so
also have a chronograph on it, but that chronograph doesn't have the capabilities of HabEx. It stops short about a factor of 10 short of what HabEx will be.
but will the success of what it does enable you to narrow down your own technology for HabEx?
Yeah, it's a very important proving ground for these future.
Proving ground, that's a good way to put it.
That's right.
Okay, good. All right, well, that's awesome. So we, with HabEx, I've asked this question of the other missions as well. Are we talking about and I'm pretty sure you're going to say star shades, but is there anything that we're going to have to invent that doesn't exist now? That was true with JWST. Some stuff had to be invented and designed before the thing could be launched. Is any of that happening here with HabEx?
Well, I think probably the most important thing once we talk about a chronograph is in terms of an invention, would be an ultra stable telescope. The optics themselves don't have to be perfect because the DM, the deformable mirror, will allow you to compensate. But
so more stable than most space. I mean, it seems to me like space telescopes, almost by definition, are stable, aren't they? I mean, they got these gyros and momentum wheels.
Look at Hubble. The secondary mirror in Hubble moves with every orbit around the Earth, and it moves by probably by microns.
So, okay, you're talking about the actual mountings then on the telescope itself, as far as stable.
The shape of the mirrors and the mirrors moving relative to each other. The shape of the mirrors has to be stable to subatomic levels, and the motion of the mirrors relative to each other has to be stable to kind of tens of nanometers, which is atomic times 10 maybe.
Okay.
So this is much more stable than any telescope any large telescope anyway that's ever been flown.
The point to emphasize the point that Stu is making is that see if I have this right, Stu. The whole system, the coronagraph and the optical telescope assembly and any instrument you put behind them, has to be treated as an entire, highly stable system.
Yes.
Everything has to work in a vastly complicated and extraordinarily high precision system to be able to achieve the kind of goals that Leslie was speaking about earlier, being able to distinguish the extremely faint star from an extremely faint planet from an extremely bright star that is just tiny, a very tiny distance apart, at least as viewed from Earth.
Mm-hmm, that's right.
Extraordinary mechanical, optical challenge.
Okay.
And by comparison, for example, the James Webb Space Telescope will have a chronograph, or several of them actually, and they'll be able to do a sort of part per million. See planets maybe a million times fainter than the star. So then the next step after that would be WFIRST. That's a part per billion, and then HabEx or other future high contrast imaging missions. But James Webb Space Telescope has stability that would be sufficient for parts per million, but it's not at all designed to do parts per billion kind of stability like we're talking about here.
And HabEx is parts per gajillion.
And in fact, Tony, to answer your question on that as an example, the pointing system for HabEx is not going to use reaction wheels or things like that because that introduces too much jitter.
I can imagine those things spinning would make a racket, wouldn't it?
So it's actually going to do all of its maneuvering using microthrusters for the first time.
Oh, so you're going to have a fuel component.
Right.
So that may be one of the things that limit that mission. I'll talk about that in a minute. We're 45 minutes into the hangout, and we still haven't talked about star shades. I want to talk about star shades. Who wants to give us a?
That? Maybe Stu Shacklin would like to talk about star shades.
Yeah.
Just off the top of my head.
Okay, so
why don't we start with that video? Yeah, that'd be
yeah.
great.
Here we go. Let me get push the play button.
This shows the star shade concept. And let's see, it's going to show that the star shade is furled up, and because it has just emerged from the shroud of the rocket, so it's in space, it's furled up and it has to unfurl, and it's going to end up being something like, well, for HabEx it'll end up being about 72 meters in diameter. The one shown here is about 34 meters in diameter, so about half the size. So out come these petals, which I'll tell you about in a moment, and then out comes this central disk. And it's really clever, and the way it deploys is the petals, which were all packed next to each other, they deploy and they end up being flat. So this is a nearly planar structure when it's all done. It's 34 to 70 meters, depending on the mission, meters in diameter, and it's going to fly away, and it's going to move itself and position itself in front of the star. And this is where you'll start to see the disadvantage of the star shade, is it has to be positioned every time you want to look at a new star. It has to be repositioned to block out whatever star you want to look at. And so it blocks the starlight and lets you see the planets next to the star. This part of the video is showing a test that we did a few years ago at Northrop Grumman Astro Aerospace here in Southern California. And it shows the petals that we had wrapped around this truss, and they come out and they deploy. And they stiffen themselves up. There's some ribs that pop out in the back. And then this is showing how that truss actually deploys. And this is a truss that was designed for space satellite telephone communication, actually. And normally it would have a parabolic mesh reflector in the middle, but we used it by attaching these petals to the side of it and then showing that it deployed and that it met all the accuracy requirements that would be needed for the star shade.
Cool. How much are you going to pay all those minions to go out there and do the
they probably drew some overtime because they were working around the clock too.
Just kidding. Okay, well that's amazing. I love looking at that stuff. This is like really a great technology. But yeah, there's some disadvantage. So first of all, when you here's the deployment. How far away is this going to be from this?
Right. So for HabEx, the distance from the star shade to the telescope will be about 125 million meters, 125,000 kilometers. So that's actually a good fraction of the distance to that L2 orbit, about a tenth of that distance.
Okay. And will it have micro thrusters on it too, or how will it move around?
The star shade for HabEx will probably have what's called solar electric propulsion.
Ah, okay.
And so those are there's a gas that gets accelerated. It takes a lot of power, so that there will be solar arrays probably mounted on the star shade itself, and that will provide the power. And then there'll be conventional thrust too that you use to keep the star shade very precisely positioned in front of the star.
So you were talking about how stable the optics and things need to be mounted and how securely. How about the pointing of that star shade with respect to the spacecraft? That seems to me like that's got to be pretty okay. High tolerance too, right?
Right, good question. So when you use the star shade, first of all, you block the light before it comes to the telescope. So that's the big advantage, is now you can just have a conventional telescope. All the stability requirements on the telescope are kind of just back down to normal imaging requirements. None of this atomic level stability, because you've thrown out the light before it ever was able to hit those imperfect optics. But yes, the star shade has to stay aligned, and the precision requirement is pretty tight. It's designed so that it has to stay within about a meter laterally of the line of sight. So there you are at 125,000 kilometers, and you're positioning it plus or minus 1 meter back and forth. As far as the distance, that can drift quite a bit. That can drift hundreds of kilometers before it matters.
And just make a quick comment on the shape. Why does it have those petals?
Right. If you go down, to, let's see, about page 9. Let's see. I guess page 9 of the Starshade presentation.
Okay, let me get that up. Page 9, dude. There we go. I hope we can see it. Goodbye.
Let's see the bottom.
Goodbye.
So what happens? What if you just had a disk? The naive thing would be to say, well, let's just fly a big disk that blocks the light of the star, but it has to be small enough to see the light of the planet, which is off to the side. You can almost see the planet there in the picture. What happens is that disk has edges all around it. The circular edges would bend the light back right onto the axis, right where the telescope is, and you end up with a bright spot on axis. So it's exactly the opposite of what you want to do. You can end up with a spot that's as bright as the star, right on axis. And so the idea of the star shade is to not have those edges around the
yeah, these little things here are bad. These little circles.
Well, the little dot in the middle is where the star shade would be, and that's bad. I mean, I'm sorry, that's where the telescope would be. That's where all that light has just been diffracted. So the idea of the star shade is that you effectively kind of smooth out that function so it doesn't have a sharp edge around the outside of it, and then you shape these petals so that the light gets diffracted away from the middle, and you end up with a very dark shadow in the middle.
Okay.
It's called an apodization function, and the petals provide that function.
Okay. All right. Well, before I get to questions, which there are quite a few in the queue here that I want to get to, let me just say, okay, so this is our second hangout with the HabEx mission from a year ago. What sort of progress have you made over the last year that's noteworthy, and are you on track for the Deckies coming up? Who wants to make a comment on that? Stuart, Paul.
Actually, is this our first second HabEx?
Yeah, we had a HabEx with different people a year ago where we talked about what the mission was and some of the principles behind it. Now I want to just give a little update on how things have gone the last year.
I can give you a quick update on the instrument, which is that there wasn't an instrument a year ago.
That's always progress to now have one.
The star shade has been designed and toleranced. The instruments have been designed, kind of past the conceptual stage to where we can do error budgets and evaluate performance of the instruments. There's been a design reference mission, so we know now kind of the sequence of stars that we want to look at least for the exoplanet part of it. So those things are all new over the last year.
And the science case, this would be a Leslie and Paul question. The science case continues to become increasingly sophisticated, which feeds into the increased sophistication.
Do they keep adding, is it got scope creep? They keep adding things they want to do?
Oh yeah, as they should. This is what scientists do. And also they've helped NASA identify key technologies, particularly, not exclusively, but particularly for instruments and the mirror systems and the Chroma Graph that need to be developed. So that's an absolutely key activity we've been talking about. And in round numbers, it's 20 to 25 years between the time, a couple of you guys mentioned this, between the time that the mission is really starting to get well studied and the time of launch. And this period of time, much of that time, is devoted to developing the technologies. And that's what we are well into, at least a couple of years into now, is technology development.
One of the things that we've had to be wrestling with is how, the telescope structure and design that Stuart's been talking about had very particular requirements, very particular things that it had to do. One of the things that we had to work out was how to make those general astrophysics instruments work with that design, right? Because we wanted to coexist, but yet still provide a series of capabilities that were compelling enough to the community to make it a very attractive facility for general astrophysics as well. And we believe we've now got to a point, due to some very hard work by some of the folks at JPL, we've now come up with a series of designs for those instruments that appear to deliver the requirements that we laid on it. And we've tried not to engage too much in the science scope creep too much. We've tried to limit it to the things that we knew were going to be
Exactly.
But it's a danger, right? You're building this thing that's so cool. It's great.
No, we're not adding infrared. No, go sit down.
Exactly.
Well, it's an important couple of simple metrics. And again, this is way oversimplification, so apologies to my colleagues here, is that the two designs to which our colleagues were referring for HabEx are, again, in round numbers, twice to 3 times the diameter of HSD, which of course still is functioning well and still turning out first-class science. So have somewhere in the neighborhood of 4 to maybe almost 10 times the collecting area of HSD, and then 2 or 3 or 4 generations of new instruments, of new technology, new detectors. that would be put on board it. So it's going to be a major, major increase in capabilities over HST, and the two instruments cover about the same, roughly the same wavelength. So this would be a huge advance in UV optical, maybe a little bit of IR, a tiny bit of IR astronomy. This would be a huge leap in capabilities.
It would be orders of magnitude improvement in throughput. Yes.
Yes.
Yeah.
Okay, well, I got to get to some questions because we only have a few more minutes left. I want to make sure we get some in. Bo Diddley is asking, won't star shades be vulnerable to space dust? Because if so, he's offering also that he would gladly go up there with duct tape. So what about that? Are you worried about these big giant things spread out in space getting holes in them?
Yes, there's two aspects of that. Dust, yes. Dust can accumulate on the edges, which we don't care about what happens on the surface, because the sunlight will always have to be behind the star shade. So if the surface gets dirty, we don't care. But the edges, though, have to remain very clean. So a little piece of dust that's let's say we had a piece of dust that's 1 millimeter in diameter on the edge, that would be as bright as a planet like Earth around another star. So we have to watch out for lots of dust accumulating on the edges. And you talked about duct tape. We plan to actually have a kind of a polymer that we would put on the edges of the star shade that would, first of all, protect it and keep it clean while it's in storage, and then we would peel it off just before we launch. That's how we'll keep those edges clean. And yes, micrometeoroids will hit the star shade over the years. They'll penetrate it, and they'll make holes. And we've had to design it so that very little starlight and very little sunlight can go through the star shade. But over time, it will deteriorate to where there is some light starting to leak through it.
Now, remind me again, how far away was it from the spacecraft, the star shade?
125,000 kilometers.
Okay, so I can easily imagine you're sitting here on the L2 point with your spacecraft and your big honking star shade. Is there any danger of you guys pointing that thing and getting in JWST's way? Because that might make them mad. Say, hey, will you move that thing? Get it out of my way. That's a lot of space you guys are taking up. And it is crowded there. And it's going to be crowded there in the L2 point. I know, it's a silly question. You don't have to answer that. I was just curious.
We're carefully tracking the position to make sure it gets nowhere close to JWST.
Okay. Hugo Burnham is on Facebook, and he's got a couple questions here. How much more reliable do you expect microthrusters to be than gyros, which always seem to be the first thing to fail on spacecraft?
Well, I think that's one of the reasons why they're looking at them so hard, is because this technology, the idea of taking solid fuels and subliming them into microthruster jets, has come a long way in the last few years. And the number of things that can fail there is actually very small. So their expected reliability is supposed to be a lot higher. And the person asking the question is absolutely right. The failure rate of reaction wheels has been a thorn in the side of many a mission.
Yes, as Kepler as Kepler can attest to. Yeah. So he's also asking, and this might be a question for you, Leslie, I'm not sure. How will HabEx be able to determine the stage of atmospheric evolution on an exoplanet? If looking at Earth's atmosphere, for example, 3 billion years ago, we would see something quite different than what we would see today. Is there a way you can tell about an atmospheric evolutionary thing from the spectra?
Well, you'll certainly have some insights, but that is what a lot of the work will go into. And certainly that's part of what motivates wanting to measure as much as we can about the planet, so that we have as much broader context that can provide inputs to that interpretation. Of course, like most important is measuring the planet's orbit, knowing how far it is from the host star, so we know how much light it's getting from the host star and whether it might have liquid water. But also trying to measure its mass somehow, its actual radius. We'll have some idea about, by detecting molecules in the atmosphere, you can measure various constituents, but yeah, knowing whether that ozone is produced abiotically or biotically, may be uncertain. There are certain questions and levels of interpretation that we just might not be able to determine with the information that we'll get from HabEx, but we will definitely learn a lot of great new things.
Okay, so there's some concern in the chat about the microthrusters and the resupply and the fuel supply being a limiting factor. How long are you guys planning to have this mission? What's the operational goal for HabEx versus there's always we want to do this for 5 years with a goal of doing it for 10 or whatever it is. What are you guys submitting? What are you guys planning for? And will it be possible? We're talking the 2020s, 2030s. So maybe have some robotic rescue capability or repair capability built in?
The idea, as I understand it with those things, is yes, there will be a gas cap that you can go up and top the thing off.
First gas cap.
Yes, that's pretty much the idea.
I love it.
So the microthruster fuel cells could be replenished. Yes.
Right. No, he's actually serious. That is, in fact, I
know he's serious. I just think it's great. I think it's awesome.
All the missions have a gas cap, not like your automobile, but they all have gas caps. For their fuel supply because they were topped off before they launched.
I know, but I guess I'm asking about the design of the mission. Is it such that it's because you can't go up and give Spitzer more coolant, for example. It's just not. It wasn't built for it. But are these generation of spacecraft maybe keeping an eye on that possibility of adding more consumables?
Sure. Yep.
And maybe even repair by remote robotic means, because I don't think sending a human to the O2 point is possible at this point either. But or even by then, it probably won't be at the rate we're going. I don't know.
Well, there's the human spaceflight division is actually floating an idea for this thing called the Interplanetary Gateway, right? Which is a staging location out there close to the lunar orbit that would allow this kind of thing.
Oh, good. Oh, I hadn't heard about that. That's awesome.
We should have a gateway talk, a gateway hangout.
That would be a great. I'd never heard of it, so I'd learn a lot. That'd be great. Okay, folks. Well, I guess we're going to call it here. I just want to read a couple of comments here. Larry Keese is talking about Broomfield High School in Broomfield, Colorado. I went to Centaurus High School in Lafayette, Colorado, and I just had to comment on that. And it's my old stomping grounds. And you guys were also chatting about your favorite computers. Back in the day, my very first computer was an Apple II Plus with 2 floppy drives, 64K of memory, and a green phosphor screen. Cost $5,000. That was my first computer. So I just had to put in my 2 cents on that as well. And I also had a Commodore 64, but I never used it because I had an Apple II Plus. Okay. All right, folks. Well, I want to thank you very much for taking time out to give us an update on HabEx. This is awesome. You're getting my vote on the Deckies if I had a vote, but I don't have one. So, and also Harley is grabbing out one of our many mascots on these hangouts. What's the name of your kitty?
This one is TC.
TC.
Yeah,
okay. And we also have we have our gravitational wave rubber ducky over there. There he is. Okay. We call him Gravy. And yes, he rides on the gravitational waves of space-time.
And we're a group of gravitational wave hangout as well.
Yes, we should. That's right. There's many things happening in the world. So thank you, Harley, for setting all these up. I think next week we are going to be having our afternoon Astro Coffee Hangout, where we're going to be talking with authors of a paper who have been looking at a nova, not a supernova, that has returned after 600 years. Observations with the Hubble Space Telescope have revealed some pretty interesting things. So Carol Christian and I will be back. She'll be in Australia, but she will be here with us to discuss that next Thursday. And then after that, we have Footsteps to Mars. So we'll be back with all of these hangouts coming every Thursday at 3 o'clock. Thank you guys very much for watching. And as always, and thank you to our guests for appearing. We hope that you'll come back at some point and give us updates as the big day gets closer and see how things go with the mission. With the Deckies, that's right. All right. I'm telling you, Harley, it's going to be a thing. Just watch. Okay. Thank you all so much for watching. And as always, keep looking up.